Thanks for giving me the opportunity to talk about our MillenniumTNG project. This is a large-scale project of the Gauss Center for Supercomputing that we are allowed to carry out on SuperMUC-NG. And I would like to tell you mostly about the scientific motivation for this project, our technical accomplishments, and also, of course, a few results. Let me maybe begin with these basic observations in cosmology. These are observations of the microwave background observed with the Planck satellite. This is basically a thermal relic left behind by the hot Big Bang. And it is a treasure chest for cosmology because in this noise, there is a lot of information in it. For example, we see this in this angular temperature power spectrum that's shown here. The data from the Planck satellite are these red symbols, and the blue line is currently the best cosmological model we have. It comes under the name of lambda CDM, and you see that it goes extremely well through the data. And in these baryonic acoustic oscillations that you see here, there's really a whole lot of cosmological information. It tells us about the age of the universe, its mean density, and things like the curvature of space. For example, the location of this first peak, the angular location, tells us directly about the geometry of the universe. So this is very, very important. Now, one peculiar implication of modern cosmology is that the strange composition that we observe in the universe today. Because if you look at the matter energy density in today's universe, which is pictured here in this pie diagram, we find that only about a quarter is made up of matter. That is things you can in principle touch and which is gravitating and clustering. And most of that, 5/6 of it, is made up of collisionist cold dark matter particles. We think these are elementary particles that are not contained in the standard system of particle physics. In addition, there is a huge component of so-called dark energy, which acts like kind of an anti-gravity today. Einstein's cosmological constant, lambda, is a representative of such a dark energy component. And for basic physics reasons, we expect that maybe there should be a different physical nature of this component, different from a cosmological constant. Yet this hasn't been demonstrated yet through observational evidence. So cosmological constant is still sort of the most natural choice at this point, which is entering also the standard models. And we don't really have any evidence yet for difference to that. Now, cosmological n-body simulations, they follow the clumping of matter over the course of the evolution of the universe, and they've been proven extremely valuable to understand whether this type of picture, makes any sense, whether structures like the ones we see in today's universe really evolve out of this peculiar mix of matter and out of these initial conditions that we observe, at the very beginning, 380,000 years after the Big Bang. And here's an image that shows that in a somewhat older result by now from the Millennium simulation that shows the cosmic backbone of structure that forms the cosmic web, where you have a network of filaments, and at the cross points, big structures form, like here in the middle of the image. The biggest ones are galaxy clusters containing about 1,000 galaxies. And simulations like these, they also showed that these type of models naturally predict a cosmic large-scale structure that at least superficially corresponds very well with the galaxy distribution that is seen in real surveys, which is kind of illustrated in this plot. And this has, been a major theme of research of the past 10 to 15 years to also examine how close this correspondence really is. And, on large scales, it is actually very close, but we are now at a level of precision where we're asking, is it really exactly reproduced, or maybe there are small differences that, for example, tell us whether the dark energy is really a cosmological constant or not. We can also do simulations these days that incorporate in full the matter energy content, not only the dark matter component, but also the baryonic component, helium hydrogen gases, and how they are pulled together under the forces of gravity into this large-scale structure, but then at the centers of these yellow nodes make real galaxies. And here are images of our illustrious TNG simulations, which represent the state of the art in this respect. And they are used extremely heavily in the field now. Despite the relative youth of these simulations, more than 280 publications have already used the data we created with these cosmological simulations. And besides showing the large-scale structure distribution of matter, these hydrodynamical simulations also give us directly the morphologies of galaxies, their shapes and sizes, the amount of stars they contain, their colors, and many, many more properties. In addition, what we also learned from full physics simulations is that the large-scale structure is slightly modified by a back reaction of the baryons onto the dark matter backbone of structure. And that we are seeing in simulations like illustrious TNG. The crux is now that we need to predict how these effects pan out in much larger volumes, because that's what's going to be probed by upcoming observations, as I'll describe in a minute. So despite sort of these successes in largely explaining the basics of large-scale structure and also the basic origin of galaxies, the lambda CDM model still gives cosmologists much to think about. And at the moment, we are basically looking for cracks in this basic model, for deviations from the predictions that are made. And that would then help us to understand what is the physical nature of dark energy. Is the structure formation evolution really consistent with this strange concept of collisions dark matter? Do we understand galaxy formation as a function of time and scale? What is the origin of the so-called Hubble tension? There is a discrepancy basically between the expansion rate of the universe inferred from observations at high redshift versus those at low redshift. This could be related also to peculiar behavior, for example, of the dark energy that we don't fully understand yet. And maybe, however, this could also be related to issues in how galaxies trace the underlying matter field on large scales, because that needs to be understood if you want to infer from observation of galaxies what the clumping of matter is and how this evolves in time. And this is not trivial. We know from our previous simulation work that galaxies are not perfect tracers of the underlying matter field. There are so-called effects of scale-dependent bias that extend to very large scales, and they are modified by baryonic physics. So it is not easy to infer them correctly if you do simplified simulations with dark matter alone. Now, since I already mentioned that currently the goal in cosmology is very much to use new upcoming observational data to basically make a stress test of our current cosmological model. And in fact, there are several missions like Euclid, LSST, and WFIRST that are currently observing billions of galaxies. They will map out gigaparsec cubes of space. So this is a very sizable fraction of the observable universe. And then they aim to use the clustering of matter as a function of time and scale to infer cosmological parameters largely independently of the CMB and to check that basic cosmological model. How this is done? Well, one uses mostly the clustering pattern of these billions of galaxies. One also uses the weak gravitational lensing effect. These are very small, statistically observable distortions in the shapes of galaxies due to the fact that the light travels through foreground structures, and these foreground structures bend some of the lights and lead to distortions and magnifications of some of the images. That can be seen in gravitational lensing effects. So the goal of these missions is to improve cosmological constraints to sub% level to make this stress test and to find evidence for deviations from the lambda CDM model. And that would be evidence for new physics. And that would be truly exciting, of course. Interestingly, though, for this to be successful, these observations very much rely on theoretical predictions that are comparable to the surveys in statistical power, in accuracy, and in reliability, of course. And this, basically can only be achieved through better computer simulations that are much larger in volume of a fiducial universe that's studied, also in accuracy. And you need, for these simulations, about 1 trillion particles in the end. Very large volumes, very large memory. You need to process the data on the fly, otherwise it's just getting out of hand and getting way too big. And then you can make, hopefully, predictions for billions of galaxies that then can be compared with accuracy to these upcoming observations. And that is sort of, in a nutshell, the starting point of our MillenniumTNG project. The idea here is, in a sense, that we want to combine and build up on the successes of our previous very successful simulation projects. On one hand, the Millennium simulation from a while back, which was instrumental to put the dark matter nonlinear structures on a much more solid foundation, and also showed how physically based models for galaxy formation can be constructed on top of these simulations, so-called semi-analytic models of galaxy formation. And on the other hand, we have our full physics calculations, ELASTIS-TNG, which are state-of-the-art, but can only be done in a rather small volume so far. So what we want to do next is, and in this project, and we're in fact doing at the moment, is we first of all want to carry out a new state-of-the-art hydro simulation in a larger volume. So this is an improvement about a factor of 15. Then we obtain a volume that's corresponding to something that we have already achieved more than a decade ago in pure dark matter calculations. This was Millennium. And so we do, with our new, more accurate codes at higher resolution, a new Millennium kind of box size, MillenniumTNG dark matter, which is 8 times better mass resolution as the Millennium, the same volume. And then we have, at the same full physics mass resolution, the full hydrodynamic calculation. By comparing them in detail, we will get a precision calibration of how full physics affects the dark matter distribution. Having this in hand, we will then apply that in its yet much larger volume calculation, which we call the MillenniumTNG XXL, which has 1 trillion particles and is then a truly cosmological volume. And in this volume, we will then be able to construct precision predictions for all aspects of clustering in a very realistic way for the first time. So this is kind of the goal we're having with this project. As I mentioned at the very beginning, we are carrying this out on the SuperMUC NG through a proposal that got approved by the Gauss Center for Supercomputing. We're very thankful for this. And we have many novel aspects of this simulation procedure in our methodology is, I think, in many respects, novel and much improved. We, for example, we will produce much of the post-processing of these very large simulations on the fly. We construct merge trees on the fly. We produce an output not in the sense of time slices like this has been traditionally done, but now we are simulating such a large volume that we are outputting directly on the path-backward slide cone, meaning that this is the only thing that's actually physically observable by a fiducial observer placed into our virtual universe. We also have very sophisticated mass shell lensing output that will then allow a statistical analysis of the weak gradation lensing with unprecedented precision. And we use, and that's also unique at this for these very large simulations, a variance suppression technique by running 2 simulations that use a special statistical realization of the initial power spectrum. And by taking the average of these runs, we then eliminate fluctuations around the expected cosmological mean on the larger scales. That means basically that we're getting a very significant further statistical lever arm on our effective volume that we study. Here's a brief overview of some of the runs we've completed in the project. Most of the dark matter runs, the smaller ones, they are all fully completed, and most of the hydro runs as well. These are basically the calibration, very state-of-the-art runs still in 500 megaparsec boxes. The hydro simulation with these 860 billion resolution elements. This is the run with 2 × 4 320 cube run. This is extremely challenging simulation, very rich in data, extremely expensive, also by far the most expensive calculation that we are doing. This is executed on more than 120,000 cores on SuperMUC-NG. So it requires a substantial fraction of the machine, especially due to its very substantial memory needs, which is also basically one of the primary headaches of these ones. So here you see this, while you can do these dark matter simulations on something like 12,300 cores, if you use all the memory, we need basic an order of magnitude more for these full physics simulations. Just as a side note, so this is really, for this type of project, the main troublemaker is the memory consumption. We need to sail very close to the limit that's possible on the machines, and that is somewhere in the framework of 15 to 1600 megabyte per course when you need, say, 120,000 cores, because it turns out that for such large partitions, also the MPI libraries and other system aspects like IO buffers, of course, also require space. That is, we cannot in production, unfortunately, use much more memory still for our application code. And what we are still ongoing runs are also our trillion particle dark matter runs. They are in comparison easier to do, much easier to do than the hydro simulation, but and we've started them, but our priority at the moment is to finish the hydro simulation, which is about 2/3 or so completed on SuperMUC-NG at this point. We will also do additional calculations that add neutrinos. Neutrinos are a hot dark matter mixture. They are thought to be massive but very light. So the sum, the 3 neutrino spaces, lies in the ballpark of about 0.1 electron volt. And at that level, this hot dark matter component has still some impact on cosmic large-scale structure that needs to be taken into account. So the idea we are having is also to quantify this really accurately as part of this project, besides the hydrodynamical impact. As a side effort, in a sense, of this project, we've also published a code paper, the Gadget 4 code that we developed and pushed further specifically for this project in SuperMUC-NG, has been publicly released already last October. This is a very extensive code that contains, I think, decades of experience, and it's a very long journal paper, more than 80 pages, and you can check this out if you're interested. Here's a scaling result that we obtained with this Gadget 4 code on SuperMUC-NG. It's a weak scaling in this graph, going all the way, basically from a single core to 10 to the 5 cores, with 5 orders of magnitude, where you hold the load per core constant, and we scale up the simulation size and also the Fourier mesh that's used to very large sizes. And you see that our short-range gravity calculation basically scales perfectly on the machine. That's thanks to a new hybrid shared memory parallelization for MPI3 that we've developed on SuperMUC-NG. And I think that is actually very helpful for us also for future architecture changes that we want to do in other aspects of our codes, that we now see that this works very well. And here you see improvements in strong scaling of a different type of problem. That's also a hydrodynamical problem. See the scalability of this Gadget 4 code now is much improved to our older Gadget 2 code, which is one of the most widely employed codes in the field still. So this is sort of also, I think, a nice side product of the project, but now let me return to describing a few aspects of what's important here. So we are tracking basic galaxy formation with these simulations, and for this we need to on the fly identify nonlinear dark matter structures and the embedded substructures which represent the galaxy positions, and that we do on the fly, and then we also track how they move from one time to the next. We call this an on the fly merger tree calculation, which is for the first time done with such large calculations. The merger trees are then very complex. We track with them the formation of hundreds of millions of galaxies over cosmic time. And we also employing an improved algorithm for tracing the substructures in time. So I mentioned earlier, we are outputting the particle data and also the galaxy data directly on the path-backwards light cone. We have different light cone geometries. We can not go full sky arbitrarily deep, then the data volume just completely out of hand. So we do what also the observation campaigns do. We have a somewhat shallower full sky survey, artificial survey, then an octant. Then we have a number of pencil beams that go very deep, back to just 600 million years after the Big Bang. Here's an example how this looks like. For example, in the matter distribution, basically the observer here would be in the center of this sphere at the bottom. If you now look out on the path-backwards light cone, here this is down out to redshift 2, you see that the structure at this edge appears much less well pronounced. That's just because you're looking into the past. This is already about 8-9 billion years or so into the past history, and there, of course, many of the large galaxies haven't even formed yet. And this seamless light cone is something that we not only have for the dark matter distribution, we also have this for all the baryonic fields as well in our hydro simulation. And especially these very expensive hydrodynamical simulation, they are of course able to predict not only dark matter distribution, but directly also the gas density, the gas velocity, the stellar density, temperature of the gas, the metal distribution, shocks, magnetic fields, and also the X-ray luminosity. So that we also have for the first time on the backwards light cone, and with this we can, for example, make realistic Sunyaev-Seldovich effect predictions on top of making predictions for the galaxy formation. Just to give you a flavor of how these results look like, here is a comparison of the matter power spectrum of this A series of the calculations, and it shows extremely good conversions and is able to map the matter power spectrum over an unprecedented range of scales. And in addition, through our variance suppression technique, we can take the average over our two realizations, A and B, of the same cosmological model, and then eliminate, by taking this average, fluctuations due to higher order perturbations around linear theory, and obtain basically now this green line where cancellations up to fourth order are realized. And that allows us to get with these, cosmological volume predictions that are much more accurate than they would otherwise have been for this limited cosmological volume. This works down even to redshift 0. Now, why is this important? Well, this allows us to map out the matter, so the baryonic acoustic oscillations also in the cosmic matter density field, both with the dark matter and different galaxy samples. And here you see a comparison at different cosmological epochs between linear theory, which is in green. This would be stationary in linear theory. And in red, you see the nonlinear outcome of the simulations. If you progress in time, you see that at small scales, the first higher order acoustic oscillations, they are eventually eaten by nonlinear evolution effects. But the interesting thing is that they also show up mild nonlinear effects, even at the present day, even at the first peak, which is seen for the first time with this accuracy here, that there is a shape difference visible, starting to become visible, which it's here, and it's tiny. This is 1% only, it seems here. But the issue now is that this percent difference is really what we are caring about in precision cosmology. In fact, we can measure the peak positions now with these simulations as a function of time. We are finding that the spatial location of these baryonic acoustic oscillations at late times are shifted by up to 2 to 3%, even reaching out to the first acoustic peak. That is very important because, as I said earlier, the location of these peaks is a direct measure for various cosmological quantities, for example, for the geometry of the universe. And by mapping out the baryonic acoustic oscillation peak positions, we are hoping to constrain dark energy. So effects like these need to be taken into account and cannot be computed reliably, at least so far, from first principles. And so that's another very important reason why we need these very big simulations to precisely map them out. Here is another plot that shows a result for the predicted galaxy stellar mass function. And basically this shows the convergence between our highest resolution run, which is the red line, and the a control run with 8 times poorer mass resolution, which in blue, and then one which has 64 times poorer resolution. This is the this violet line. That's clearly not good enough. But the good agreement between the blue and red line shows us that basically the red line is probably to be trusted all the way down to 10 to the 7 stellar mass, which are basically all the observable galaxies. We more or less have nailed the abundance with this calculation. The output data volume is huge. Just to flash this, we produce very many dark matter structures in one of these 4,320 cube runs. It's about 20 billion. Halos, subhalos are combined in the merger trees. We have about 30 terabyte or so particle data, but the main output are these light counts, which weigh in for one of these simulations at highest resolution of around 400 terabyte. In addition, we have the best highest resolution weak lensing maps so far, with about 2 billion pixels in total, corresponding to an angle resolution of about 0.28 arc minutes. They are at least not very big. So in total, we're looking at about 2 petabyte for this whole project. And as I mentioned, and I don't have time to go into this, we're also doing some neutrino control simulations as well as part of the project. So in a nutshell, I tried to give you a very brief overview, mostly covering the motivation of the MillenniumTNG simulations that we are carrying out on SuperMUC-NG, and we're pretty far with this project. It combines hydro simulations, state-of-the-art simulations of cosmological structure formation that make real galaxies with even bigger high-resolution n-body calculation that track only the dark matter. And for those, we use the brand new Gadget 4 simulation code. We, for the first time, have seamless light cone outputs with physical models for galaxy formation that are large enough to be compared to the upcoming cosmological data. And just a side comment, the hydro code that you're using is our repo code. We needed to scale this up to 120,000 cores. Tuning the performance on SuperMUC was painful to do this. This was very challenging for us because these are really very tightly coupled physics simulations. They led to an intimate familiarity of us with the limitations and quirks of today's MPI libraries. So we learned a lot from this, and I think it will help us in maybe future projects that are even bigger. So thanks a lot for your attention.